Well, in the last two sessions, we have been working on the properties environment of Aspen Plus, where we have learned how to add components in the component list, explore different component databases, learned how to use method assistant tool to help identify an appropriate method, also retrieved experimental data from NIST thermodata engine, then performed property analysis for the pure component, binary system, and the ternary system. Particularly, we have been working on the property analysis of binary and ternary systems to identify an appropriate separation scheme for the azeotropic systems. And at the end, we have learned how to perform property analysis for electrolytic systems and analyze the solubility of solid components in the appropriate solvent, and did the mixture analysis by calling the property set option from the Aspen Plus. From now onward, we will be working in the simulation environment, and today we are going to have the first sessions on the pressure changing equipment. Before diving into simulation of pressure changing equipment, I invite you to another lecture already recorded and available on my YouTube channel to get familiarized with the simulation environment, particularly how to draw a flow sheet. I will recall that video and add a snapshot of the relevant video for your help. So let's jump into the simulation of pressure changing equipment. Before actual simulation, let's have a look on some key terminologies that are involved in the simulation for today's session. And these terminologies are primarily from the fluid flow textbooks. You need to mind these terms before actual simulation. The first thing is the characteristic, or we call the performance curve. That is the graphical representation of the pressure changing equipment performance that shows the relationship between key parameters including capacity, or we call the flow rate, head, efficiency, and the power. Then the fluid power, that is the power delivered to the fluid by the pump itself. Then there is another term called the mechanical or the brake power, that is the actual power delivered to the rotating shaft. Most of the time, this is the power delivered by the electricity or the electrical energy. This is the power delivered to the rotating shaft of the pump or the turbine to account for the mechanical losses. Then the head is the height of the fluid column equivalent to its pressure energy. We have two terminologies related to the net positive suction head. First is called the available net positive suction head, and the next is the required net positive suction head. Net positive suction head available is the absolute pressure available at pump suction, whereas the net positive suction head required is the minimum suction head required by a pump to avoid the cavitation. Here you can see the relevant mathematical formulations that can be used to calculate the net positive suction head available as well as the net positive suction head required. Most of the time, an empirical relationship like this are used for the calculation of net positive suction head required. Then we have two terms related to the efficiency of the pressure changing equipment. One is the isentropic efficiency and the other one is the polytropic efficiency related to those corresponding processes. The isentropic process is the thermodynamic process that does not involve any heat exchange, and during that process there is no change in the entropy of the process. Whereas in the polytropic processes, it is common to have either heat flow between the system and the surrounding, or due to irreversibilities or the frictions, we end up with having a quantifiable change in the entropy. Then you need to mind the difference between normal volume and the standard volume used either to define the component flow rate or the compositions, or the results are presented. The normal volume is the volume of the gas that is measured at 0 degrees Celsius and 1 atmospheric pressure, whereas the standard volume is the volume of the gas that is measured at a reference temperature. And most of the time, this reference temperature is taken at 15 degrees Celsius or 20 degrees Celsius, depending upon the standards or the regions where these terms are used. Then there is a very useful term, and that is the cavitation index. Cavitation index is the dimensionless parameter used in fluid flow to predict the onset of the cavitation. And that cavitation index correlates the inlet pressure, the discharge pressure, and the vapor pressure, and generally it ranges between 0 and 1. The equipment available in Aspen Plus to simulate different pressure changing equipment are the pump, compressors, valves, pipes, and the pipelines. Pump can simulate the characteristics of a pump given that we have defined a pressure development. It can calculate the power required to deliver that pressure development, or in case if the power is defined, then we can determine how much pressure will be developed. Also, the same model can be used to simulate the hydraulic turbines, where the pressure gradient across the turbine can determine the power delivered by the turbine. Then there are two models related to the compression. One is the simple one single stage compressor, and the other one is the multi-stage compressor. Single stage compressor can be used to simulate a single stage compression as well as the gas turbines. This model can simulate the polytropic compressor or the turbines, polytropic positive displacement compressor or the turbine, or it can simulate the isentropic operation across the compressor or the turbine. In multi-stage compressor, it can assume multi-stage polytropic compression process or the polytropic positive displacement compressor. Similarly, the isentropic compressor or the isentropic turbine operating in a multi-stage. Aspen Plus has already introduced intercooler as well as the separation of the condensate that happens because of the cooling and the compression process. So rather than installing a separate interstage cooler or separate flash column, this model already has integrated these two units inside a multi-stage compressor. Then there is another unit to simulate the control valves, and the valve calculates the pressure drop or the valve coefficient of the control valves. Then there is a segment of the pipe. The pipe can calculate the pressure drop and the heat transfer in a single pipe segment. All the pipe fittings, including non-control valves, T's, elbows, or similar kind of fittings can be simulated inside this model. For pipeline, it can calculate the pressure drop and heat transfer in a pipe segment or the annular space or a pipeline. So these are different unit operations available in the model palette pressure changing equipment. In this session, we'll be working on a pump, single stage compressor, and multi stage compressor, as well as we'll solve the control valve and the pipe segments. There are other useful simulations regarding pressure changing devices, particularly to determine the line sizing of any equipment, develop data sheet of the pumps for a given operation, but these topics will be subject of a different session somewhere in the future. Also, using the same models, we can optimize the diameter of a pipe, causing a minimum overall cost, including operational cost and the capital cost of the pipe. But again, this subject will be a subject of a different session. So let's jump into the first exercise of this session, and that exercise is related to the water pumping activity. So the exercise is 40 tons per hour of water with a temperature of 20 degrees Celsius must be pumped from 1 to 6 bar. So for this activity, we are asked to determine the electricity requirement of the pump. If the pump efficiency is 70%, then the pump characteristic curve, that is the relationship between capacity of the pump and the head developed, provided by the producer as it's given in the below table over here. Considering the same efficiency 70% as of the point number 1, calculate the discharge pressure had developed and net positive suction head available. Then we asked to determine if the electricity price is considered as $0.0775 per kilowatt hour. Then determine the pumping cost as dollars per hour. Then we have to do another exercise. If the electricity source is a natural gas, then considering energy source efficiency factor of 0.58 and considering EU 2018-2066 emission factor data source, determine the rate of CO2 emissions for this pumping task. So these are all the exercises related to the pump model in Aspen Plus. Let's jump into the Aspen Plus and solve this exercise. Let's open a new simulation without any default template. Since we are working only with a single component water, let's define water. Proceed to the property method. From property method, let's call all the methods related to the water simulation. And let's choose the first method, IAPWS95, that is commonly used for the simulation of water systems. With the definition of components and the property method, we are good to run the properties environment. Let's proceed to the simulation environment. Here the first task is to define the flow sheet. For the flow sheet, we need a pump. Let's name it as a pump. And inlet stream, let's call it inlet. And a discharge stream, let's call it discharge. To get rid of the selection tool, either you can press escape button from the keyboard or you can tool this cancel insert option. To smoothen the presentation of the flow sheet, let's click Ctrl A to select all the flow sheet and then Ctrl B and Ctrl J to reroute the streams and align streams with the blocks. Or you can use these helpful tools, reroute stream and align, for better presentation of the flow sheet. With this flow sheet is defined, let's enter the inlet stream to define the parameters of the inlet stream. The temperature is given as 20 degrees Celsius and pressure is 1 atmospheric. It's a good practice to define the composition on the right side and the total flow on the left side, although you can define the total flow of the components in the composition that can simultaneously define the total flow as well as the composition. For better practice, let's define the composition over here. It's a pure component and the total flow rate that is given on the mass units 40 tons 40 tons 40 tons per hour. So let's select the appropriate unit of 40 tons per hour. With this, the inlet stream is defined. Next, we can proceed to the block where we can define the performance of the block. Here we are asked to define the discharge pressure of 6 bar. If you are working with the pump, then you can use this model, or if you are working with the turbine, then you need to click this radio button. Also, apart from defining the discharge pressure, you can define the pressure increase, that is the difference between discharge pressure and the inlet pressure, or you can define a pressure ratio, that is the ratio of the discharge pressure and the inlet pressure. Or if you have the power inputs, then you don't need to define the either pressure, you can directly define the power. So you can define the power to determine the pressures, or you can define the pressures to determine the power. Alternately, if you have the manufacturer data of the performance curve, then you can proceed to this radio button. We'll do this in the next question of this exercise. But the efficiency is given, that is 70%. Here you can enter a number between 1 and 10 to the power minus 15. So that should be a fraction 0.7 to represent the 70% efficiency. If the driver efficiency is available, then you can define the driver efficiency over here as well. That is the efficiency between electrical energy input and the mechanical energy produced for the shaft. So that is the efficiency between these two parameters. One useful option is to see if we are working with the liquid phase for pumping. Otherwise, you can have a vapor liquid phase as well, or vapor liquid liquid. But for a simple subcooled or incompressible fluids, you can use the liquid. It will avoid unnecessary burden on the Aspen Plus to determine the phase equilibrium calculations. So with this, we can run the simulation. Let's proceed to the results. You can view the results either from here, or you can view the stream summary results from this option. Let's proceed to the results from here. Here are the results of the pump block, where the fluid power is 5.03, but the brake power is 7.19 kilowatts. So the difference between the fluid power and the brake power is directly onto the efficiency of the pump. Since we had defined the 70% efficiency, so the fluid power is 70% of the brake power. If we had defined the driver efficiency, then the electricity requirement should have been higher than the brake power, and the brake power should have been higher the fluid power. So that means for the given activity, we require 7.19 kilowatt electrical energy to deliver 40 tons per hour from 1 bar pressure to 6 bar pressure. Also, it has calculated the volumetric flow rate, the pressure change. The net positive suction head available is calculated as 10.11 meter kilogram force per kg. Head developed is also determined. The pump efficiency is given as the input. Net work required is the same as the electricity or the brake power in this case, and it has also calculated the outlet temperature. You can also view the stream results either from this option, or to view the stream results you can go to the home tab and view the stream summary. It will land on this table where all the streams corresponding to that block will be listed. How to read this table? By default, a brief description of the streams is given in the upper section, where it also defines that stream source and the destination. For example, the source of the inlet stream is no equipment, but the destination of the inlet stream is the pump. Whereas in case of the discharge stream, the source is pump and it's going nowhere. The stream class is also mentioned. We will come back to this option. What does it mean by stream class in a future sessions? But more important results are in the mix upstream, where you can identify the phase, the temperature of all the streams, the pressure of the streams, mole fraction of a liquid, a vapor, or solids are also given. Since this is a liquid phase, so the molar liquid fraction is 1. You can also notice different energy parameters, including the enthalpies, entropies, densities. You can notice the enthalpy flows are in the minus. Otherwise, generally in commonly available stream tables, you can notice a positive magnitude value of the enthalpy flow or the specific enthalpy. Aspen Plus assumes total enthalpy as a sum of the formation enthalpy as well as the sensible heat required to raise the temperature from the standard conditions where the enthalpy of formation is considered. So that's why, because of the higher negative value of the enthalpy of formation, you see a negative number in this case. Otherwise, in commonly stream tables available with us or in the textbooks, you see this number is the positive. You can also view the molar flow of all the components. Since in this case we have only one component, so one component flow rate is given. You can also notice the mass fractions. The volumetric flow rate is also given. In the default template, Aspen Plus assumes all the phases and lists the corresponding phase stream summaries in the bottom. If there was a vapor phase, then it should have represented a vapor phase over here as well. If these stream results are not sufficient, then you have the opportunity to show several other stream properties. For example, let's view the viscosity of the stream. You can enter a viscosity, and several viscosity options appear to add in the stream table. The kinematic viscosity, the mixture viscosity, viscosity of a pure component, even you can add the viscosity index, or you can check other related options. Let's add the viscosity of the pure component. You can add to the stream table. You can view this property is added at the bottom, whereas the upper options are already available in the template. So you can add to the stream table. At the bottom, you can notice a stream table representing the viscosity of the pure water. So that is at the inlet 1.00016 centipoise, but in the discharge stream, a slightly lower viscosity is presented. So probably related to the slightly higher temperature. So this is how you can simulate the pump in Aspen Plus. In a future session, we will also work on developing the data sheet for the pump. One thing to notice is typically it's not important to define the discharge pressure of the pump. Rather, the purpose of the pump is to deliver a certain pressure in the downstream unit. Then, because of the pressure drop between the downstream unit and the pump itself, either from the pipe or the fittings or other minor units, including the instrumentation, a slight pressure drop happens between the downstream unit and the pump, and the discharge pressure from the pump should be higher than the required actual pressure in the downstream unit. So that is the subject of exactly the relevant case study. We'll come back to those case studies in the future sessions as well. So that was the first task of this exercise. The second task is the pump characteristic curve provided by the manufacturer is given. So we have to use this pump characteristic curve to determine the discharge pressure head developed and net positive suction head available. And for this case, the pump efficiency will be assumed as same, the 70%. So let's add the performance curve to the same pump. For that purpose, I can simultaneously view both sheets. so that we can directly enter the data from the table into Aspen Plus. To add the performance curve, let's go to the pump setup, and rather than choosing a discharge pressure, let's use the performance curve to determine the discharge conditions. And when you use this radio button, immediately the performance curve tab becomes active. For performance curve, you can add either the tabular data or the performance curve in terms of polynomial. For that purpose, you need to know the degree of the polynomial and the corresponding coefficients. So here the performance curve is given between flow rate and the head. So let's use the performance as the head and the variable is the volumetric flow rate. We also need to select whether we are talking about a single performance curve or we have the multiple performance curve, whether the performance curve is at operating speed or at the reference speed. Depending upon the type of information you have, you need to choose the appropriate option from here. So let's choose the single curve at operating speed and enter the curve data option. Here first select the appropriate units. In this case, the head is given in terms of meters and the flow rate is given in terms of cubic meter per hour. So let's use this option, cubic meters per hour. And for curve number 1, let's add the values of the head and the flow rates. So for 60-meter head, 57.5 meter, let's enter all the data. And corresponding flow rate as well. So with this, we have defined the performance curve and we don't need to define anything else. Let's open the results tab first to view if there is any variation in the results. Previously, defining a discharge pressure of 6 bar across the pump, the power requirement was 7.19 kilowatt. So now we are not going to define the discharge pressure, rather the performance curve is given. Let's run the simulation and see if there is any difference in the power requirement. So the power requirement has increased from 7.1 kilowatt to 7.6 kilowatt. So that means with the actual operation of the pump given by the information by the manufacturer, we have to have higher power delivered to the pump. At the same time, the pump discharge pressure has increased from 6 bar to 6.27 bar. You can also notice the available net positive suction head and the head developed. So this is how you can define a performance curve for the actual operation of the pump. The third exercise is, if the electricity price is considered as $0.0775 per kilowatt, then determine the pumping cost. So for that purpose, we have to attach a utility stream with the pump and then define the cost of that utility to determine the cost of the utility. Go to the setup option and in the fourth tab under utility, let's add a new utility. Name the utility stream. Let's call electricity. By default, it has given an option of electricity. So let's choose this electricity as a utility. If you have noticed, immediately in the utilities folder, this freshly defined utility has been added. So let's go to this utility and see the purchase price for the utility. So this is exactly the same as given in the problem statement. So we are happy with this utility cost and we can run the simulation once again. You can notice the results under the results tab. Here all the informations related to the utility are provided. The duty is given and that duty is exactly the same as of the power requirement. The cost is listed as $0.588 per hour. Meanwhile, the CO2 emission rate is also calculated and displayed over here. So the required answer was to determine the cost of the pumping, and that is $0.588 per hour. In the next question, we are asked to determine the emission rate provided that the source efficiency factor is 0.58 and the template is EU20182066. Let's make a slight modification in the utilities to match the required template. Go to this carbon tracking option under the utility. So here CO2 emission factor data source is by default US title, but we need to have another data source EU201A2066, and the fuel is natural gas in this case. You can move along the drop list and identify the natural gas. Here it's given as the natural gas. Mind the difference between natural gas and the natural gas liquefied form. So we are given with the natural gas. The energy source efficiency factor is 0.58. Still, it will remain the same as of the question. So we are good to run the simulation. Let's run the simulation and view the results of the emission rate. So the emission rate in this case is 2064 kilograms of carbon dioxide per hour. So for the given pumping exercise, we have to have an operational cost of $0.588 per hour, and this pumping will result in the CO2 emission rate of 2.64 kilograms per hour, provided that we have specified a data source given by the European template with the source conversion efficiency factor of 0.58, and the source for the electricity production is the natural gas. So this is how we can simulate a single pump when the performance curve of the pump is given and we are asked to determine either the power requirement or the utility cost or the CO2 emission rate. Let's proceed to the next exercise. Here we have to have the simulation of water flow system. For water flow system exercise, it is required to deliver 10,000 kilograms per hour water from tank 1 to tank 2. Those are located 2 kilometers apart. Water available in tank 1 is at 25 degrees Celsius and 2 atmospheric pressure. The schematic of the pumping network is given below, where the water is taken from pump 1, passing through a control valve, then a pipe segment including certain fittings, then a control valve after the pipe segment before the pump. Pump will deliver a certain pressure to accommodate the pressure drops between the two tanks, and after the pump, another control valve followed by a pipe segment with the fittings followed by a control valve before the water enters the second tank. Since Aspen Plus is a steady state simulator, so for that purpose, we have to have the inlet stream of the tank 1 and the discharge stream of the tank 2 as well. So for this pumping network, we are asked to use the stream NBS as the property method, and we are asked to view the stream summary and report the pressure drop across all segments of the network. We're asked to determine what is the flow regime in each pipe segment. Here, from the flow regime, we are about whether the flow is in the laminar region or in the transient region or in the turbulent region. We're asked to plot the pressure profile in the pipe segment and what is the likelihood of cavitation in the network. So let's enter Aspen Plus and solve this exercise. Let's display the two sheets simultaneously. To simulate this exercise, all the related information for this pumping network is given at the bottom. So how to simulate the tank or the valves, all the necessary information is provided in this table. Let's first enter the properties environment to define the property method, and this time the property method is the stream NBS. With this selection, just run the properties environment to retrieve all the results, then enter the simulation environment. In the simulation environment, first we have to draw the flow sheet, and then we can come back to the input conditions of the streams and the individual unit operations. Let's momentarily delete this flow sheet. To delete, Control A to select all the flow sheet, and from the keyboard you can delete. Let's first pick all the models involved in this flow sheet, and then we can connect all the units with the streams. So first tank, you can find it in the mixer, name it as tank 1. Then we have a valve from the pressure changing devices, valve 1. You can pause the video for a moment to draw this flow sheet. From my side, I will speed up the video. So the complete flow sheet is drawn. Let's escape to get rid of the selection tool. Press Ctrl A to select the complete flow sheet, and then you can reroute and align for the better presentation of the flow sheet. Or you can use the shortcut keys Ctrl A, Ctrl B, and Ctrl J. So the flow sheet is complete. Let's enter the information of the inlet stream and the units across the flow sheet. For inlet stream, the temperature is given as 25 degrees Celsius and the pressure is 2 atmospheric, assuming the same pressure inside the tank 1. Let's define the composition on the right and the flow rate on the left. It's 10,000 kg per hour. So inlet stream is defined. The degree of freedom for the tank is 0. We don't have to define anything inside the tank. For the valve 1, let's have a look on the input informations of the valve 1. So calculate outlet pressure for specified valve opening in the rating mode. So proceed to the valve 1. Either you can double click on the flow sheet or you can navigate from the navigation pane. For the valve operation, either you can use the calculation type of adiabatic flash for specified outlet pressure, or you can use calculate valve flow coefficients for the specified pressure, or you can calculate outlet pressure instead of the valve coefficient for the specified valve. And you can assume the three modes of the calculation. First is the simulation one, the second mode is the design, where the target is to determine the flow coefficients, and in the rating mode we can provide the geometry or the flow coefficient, and Aspen Plus can calculate the outlet pressure. So let's use the third rating option, and for rating option we are given with the valve opening of 50%. If the flow coefficient was provided, then we could have used the flow coefficient. Then we need to define the valve parameters for this opening. For purpose, first we need to define the type of the valve. For this valve, the type is butterfly. Manufacturer is Niels Jamsbury. Only one manufacturer is listed. The style of the valve is ANSI class 300 and the pipe size is 3 inches. By defining this information, Aspen Plus retrieves all the manufacturer information to simulate the valve. And that information is primarily the performance parameters of the valve of this specific valve against the valve opening. So valve is defined. Let's enter the valve informations for valve 2, 3 and 4. So still in the valve 2, we need to define the valve parameters to determine the outlet pressure. The flow opening is 50%. For valve 2, the type is ball valve. Manufacturer is still the same. Style is metal seated full port and the size is 3 inches. For valve 3, we can define the input specifications. So calculate the discharge pressure. Opening is 50%. Valve type is globe. Manufacturer is the same. And style is V810 equal percent flow. And the size is 3 inches. Let's enter the information of valve 4. Calculate outlet pressure for 50% opening. Valve parameters are the globe valve, same manufacturer. Type is V810 linear flow this time rather than equal flow. And the size is 3 inches. So all 4 valves has been defined. Now the missing information is related to the pump and the two pipe segments. Let's enter the pipe segment information first. So this pipe segment can be used either for the fluid flow or you can use same for the solid conveying. You need to define the pipe length. Let's equally distant the two pipes, half before the pump and half after the pump. So before the pump, let's take 1 kilometer. We need to define the diameter information. We don't have the exactly inner diameter, rather we are provided with the schedule information of the pipe. Material is stainless steel, schedule 40, and the nominal diameter is 2.5 inch. We are not given any information related to the roughness of the pipe. Let's assume the same as of the default. If you have a better guess of the pipe roughness, then you can define the pipe roughness over here. This is a very critical parameter to determine the pressure drop. Further, the pipe insulation to ensure adiabatic flow conditions, it will assume the pipe is formally insulated and there is no heat loss between system and the surrounding. Then we are asked to define certain fittings on the pipe, and those fittings are screwed connections rather than flanged connections. There are two gate valves, one butterfly valve, six large 90 angle elbows, and 10 straight T's installed on the pipe. So the pipe 1 information is defined. We have the same information for the pipe 2. Let's define over there. Length is 1 kilometer. Material is stainless steel, 40 schedule, and nominal diameter is 2.5 inch. We have to define the adiabatic flow. There are two gate valves, one butterfly valve, 6 elbows, and 10 straight T's. So two pipe segments are defined. Let's define the pump. For the pump, only one information is given, that is the discharge pressure. So we can use the discharge pressure of 3 bar. No information is provided for the efficiency. All the required information is complete. You can check the status at the bottom. Required inputs complete. Before entering the simulation, I would like to call the control panel to see how Aspen Plus simulate this flow sheet. Let's open the control panel from the home menu. The sequence of the simulation will be shown over here. Apparently it's not visible. You can press this step through option or the step through option from the main ribbon to step one step ahead. Although it has solved first unit of the flow sheet, but still you can notice the sequence of the units that Aspen Plus will use to simulate. So Aspen Plus will simulate tank 1 first, then valve 1, pipe 1, valve 2. At those moments you need to mind the difference between the equation oriented simulator and the sequential modular simulator in Aspen Plus. By default, all the calculations are made using sequential modular solver. So in this case, Aspen Plus solves a stream first. It can be anywhere inside the flow sheet depending upon the sequence, and then gradually simulates unit by unit by unit. But in the equation oriented solver option, Aspen Plus builds a large matrix involving all the necessary calculations and degrees of freedoms and simultaneously solve the complete flow sheet. So in circumstances, the equation oriented solver is more appropriate to use, but by default, relatively simpler simulations can be performed with the default sequential modular simulator. Having a good idea of this sequence is particularly relevant, especially if you are talking about a recycle loops or multiple recycles are attached in the simulation. So then you need to figure out what unit will be the first one that Aspen Plus will solve, so that you provide enough information as a first guess, and Aspen Plus can recalculate the informations of that necessary unit or the tiered stream. We'll have such exercises in the future sessions, but let's first focus on this. We are ready to run the simulation. Let's run the simulation. Run is successful and you can view the status as results available. So once these results are available, let's have a look what are the questions to be answered in this case. So first one is view the stream summary and report the pressure drop across all segments of the network. You can view the stream summary either individually across all the units, that is the option just above the summary and below the results of that unit block, or for the complete flow sheet, you can go to this stream summary option over here. Here you can use any default template, all streams or only the boundary streams or only the feed streams. For example, if you choose the boundary streams, it should display only the results of the two streams, one at the inlet and one at the outlet. Or you can use the other options. You can switch between other options right from here. You can choose to view only the results of the feed stream. That means there is only one feed stream for the complete flow sheet. Similarly, you can scroll across different options. So let's view all the stream results. You can hide this navigation pan to have a better view of the stream summary. Here you can notice the sequence of the streams from 0 to 9. These are all the streams, and you can view the temperature of all the streams, the phase of all the streams, and the pressure across all the streams. So we are asked to notice the pressure changing across all the streams. So the inlet pressure is 2 atmospheric, that is 2.02 bar, and the tank outlet is still at the same pressure as the tank inlet. But after that, a valve was installed and there is a slight pressure drop between the valve, and you can notice the valve pressure drop is around 0.013 bar. Then we have a large pipe segment where different fittings were installed on the pipe. So there is a significant pressure drop in the pipe segment, and there is a valve after the pipe segment, and there is a slight pressure drop around 0.02 bar pressure drop on the valve 2. So since valve 2 and the valve 1, they are of the different types, so that's why you can notice a different pressure drop across two valves. Then there is a pump installed and the discharge pressure of the pump is 3 bar. So it takes the suction at 0.5 bar and delivers at 3 bar. Then after the pump there is a valve, then the pipe segment with several fittings, and then a second valve after the pump, and there is a second storage tank at the end of the network. So the discharge pressure of 3 bar drops in a sequence after the pump, and in the discharge tank 2, the available pressure is 1.12 bar instead of 3 bar that is delivered by the pump. So primarily it looks like the purpose of the pump is just to provide a sufficient pressure to handle the pressure drop across all the pipe networks. For real-time simulations, you need to mind if the required pressure in the tank 2 is other than this 1.12 bar, then you have to account for all the pressure drops between the pump and the pump delivered to the tank, so that all the pressure drops between the pump and the tank are added to the pump, so much so the pump delivers sufficient pressure to meet the requirements of the discharge unit. You can notice mole fractions of different phases, some information of the energy values, and information of the composition and the flows, and you can also view different properties. One properties would be very much relevant in this exercise is the vapor pressure. So if the vapor pressure approaches the pressure of the pipe, that means that is an indication where the cavitation can form or the bubbles can form, leading to a vapor formation from the liquid phase. Though apparently we are not expecting any cavitation in this case, but still it's good to have the vapor pressure of all the streams labeled over here. You can call the vapor pressure liquid vapor pressure. The alias is PL for this case. Let's add to the existing stream table and display the result at the bottom. The results should be somewhere under the folder liquid phase and in the liquid vapor pressure. So here is the vapor pressure of all the streams at given temperatures. You can notice the vapor pressure is nearly 0.03 bar at the given temperature. So that means any pressure higher than this pressure is appropriate to suppress the cavitation formation. The minimum pressure in the pipe network is zero point 0.5 bar just before the pump, whereas the highest vapor pressure is close to 0.03. So the actual pressure at any point in the pipeline is way higher than the vapor pressure. So this is how we can view the stream summary and report different pressure drop across the segments. We can also report the pressure drops for individual units from the navigation pane. For example, what is the pressure drop across a pipeline? You can go to this folder under the results. It asks whether we want to save the template because we have added a liquid vapor pressure in the table. We are not interested to save this template. So just go to this results option. Here you can notice a total pressure drop in the pipe segment 1. So pipe segment 1 is 1 kilometer long. There are several fittings installed on the pipe. So that makes an equivalent length higher than 1 kilometer. So there is a difference of 25 meters, nearly 25 meters between actual pipe length and the equivalent length. So that 25-meter accounts for the equivalent length of the fittings. It assumes the pressure drop and how much pressure drop is corresponding to the pipe length and adds that length to the actual pipe length to calculate an equivalent length. Here you can also notice whether this pressure drop is appropriate for this pipe segment or not. Generally, in a pipe delivering liquid water, the maximum allowable pressure drop that is used for the line sizing is around 1.5 bar per kilometer. So that means we are pretty much close to the actual pressure drop that is allowable for any pipe network. Also, you can view a couple of other results in the streams tab. Here you can notice the inlet pressure of the pipe segment and the outlet pressure. The temperatures are given. The mixture velocity is also given. This mixture velocity is very much relevant when doing the line sizing of the pipes. So you can notice inlet mixture velocity and the outlet mixture velocity. And the average of the two velocities can give an indication whether an erosion can happen inside the pipe or not. So the actual velocity is zero point 0.9 meter per second and the erosion can happen at 3.86 meter per second. So we are pretty much on the safe zone. You can also Reynolds number. There was a question on the flow regime. So the Reynolds number is 63,000. So that is way in the turbulent zone. So we are expecting a turbulent zone in the pipe 1 segment. You can also view a couple of other options, especially in the profiles tab, that gives the pressure drop as a sequential measure of the pipe length. If you are interested, you can also plot the pressure drop, actual pressure along the length. For that purpose, you can go to this plot options. Here you have several options. Let's plot the pressure, and that gives an indication of the pressure along the pipe. At zero length, before entering the pipe, the pressure was around 2 bar, but gradually along the pipe, the pressure drops and actual pressure becomes lower, lower, lower until at the end we have a pressure of even less than 0.6 bar. If you want to view the actual numbers, you can right click and show the tracker. That tracker, wherever you move, it will give an actual value of the pressure across the length. For example, at 1000 meter, the actual pressure is 0.524, and anywhere inside you can notice the discrete value. You can also notice the discrete values from this summary table. For example, at mid of the pipe at 500, the actual pressure is 1.26 bar. So if you are interested in the velocities, you can see the liquid velocity or the erosional velocity development along the pipe. If you are interested, you can view all the results where not only the pressure or the velocities are given, rather the density along the pipe length is given. Reynolds number is also given. There is only a slight change in the Reynolds number between inlet and outlet. So that means throughout the pipe length we have a pretty much the turbulent region. Friction factor is also calculated and the superficial velocity is also calculated. You can also notice couple of other results. For example, enthalpy and a liquid mass flow is also given. Similarly, let's view results from the valve. What are the information available there? So let's open any valve and go to the results. In the valve results, first information is about whether the valve choking will happen or not, and we are good to have a information that valve is not choked. With a 50% opening, there is a minimal probability that there will be any choking in the valve. So the outlet pressure is also given, pressure drop across the valve is given, and the choked outlet pressure is given. So if we had outlet pressure of 0.65 bar, then there was a good chance of the valve choking. But actual valve outlet pressure is 2.01 bar. So that means we are way above the choking conditions. The valve flow coefficient is also given 103. Valve opening is defined as the inlet values or the input values. The pressure drop ratio factor is 0.45. Pressure recovery factor is also given. So that information is available for the valve. Similarly, we have already gone to the pump informations. You can view the pump results as well, where the fluid power and the brake powers are given. Volumetric flow rate, net positive suction head, the head developed, pump efficiency is 0.42 in this case. The network required is also listed over here. So these are different results that you can view from here. Let's have a look. What are the questions? What is the flow region in each pipe segment? We have first seen one pipe segment flow regime that is in the turbulent region, and we are expecting the same in the pipe 2. Plot the pressure profiles in the pipe segment that we have already seen. What is the likelihood of cavitation in the network? There is a minimal likelihood because we have seen from the vapor pressure. The actual pressure is way higher than the vapor pressure, almost an order of magnitude. So that means there is a minimal chance of the cavitation in anywhere inside the pipe network. So that's all about the simulation of a water flow network. Let's jump to the third exercise of the day, and that is related to the compressors and gas turbine simulation. So the exercise is: a centrifugal compressor is used to recover the pressure drop during the transportation of natural gas between two compressor stations. The inlet temperature of natural gas is 25 degrees Celsius. The inlet pressure is 5.5 megapascal and the compressor pressure ratio is 1.5. 1 million normal meter cube per day of natural gas with the composition given in table below over here is processed. So we are asked to determine the temperature of a gas at the compressor outlet and the power requirement if the polytropic efficiency of the compressor is considered as 0.76. So for that purpose, let's open a new simulation. Go to this new simulation, enter without any default template. If you are interested, you can save the previous case study, otherwise you can ignore it. So define the components of the natural gas. Let's open it simultaneously. Let's define methane, ethane, propane, nitrogen, and carbon dioxide. So these are the components. We are not mentioned any of the property method. So since these are the natural gas components, and the simpler equation of state can pretty much simulate this system. So let's use the common one, the Pang-Robinson, as the property method. And we are asked to review the binary interaction parameter. Let's proceed to this tab, or you can go to the next. So all the inputs in the properties environment are done. Let's run the simulation and enter the simulation environment. Since this option is related to the compressor and the gas turbine, so first build the flow sheet. In the flow sheet, this is a compressor option, and the same model can be used for the turbine if you want to have a different icon for the turbine, then you can use this icon. Let's use the compressor and name it as compressor COMP. Connect the inlet line. Let's call it as inlet, and the other required discharge line, let's call it discharge. Escape to get rid of the selection tool and define the inputs of the inlet stream. The temperature is 25 degrees Celsius. Inlet pressure is 5.5 megapascal. Composition is given as mole percent. So go to this mole fraction. Here we can define the composition. Methane is 92%, ethane is 3%, propane is 2%, nitrogen is 2.5%, and CO2 is 0.5%. And the sum of all the fractions is 1. Then we have to define the volumetric flow rate of the natural gas. For volumetric flow rate, let's choose the option of volume, and the units are million cubic meter per day. So let's choose the option of million cubic meter per day. It's here, and it's 1 million cubic meter per day. So with this, the inlet specifications of the streams are defined. Let's proceed to the block options, where we need to define the informations for the compressor. So here you can use the same model for the compressor, or you can use the same model for the gas turbine. For both options, we need to define the type of the model. It has given options to make calculations based on the isentropic operation or based on the polytropic operation of the compressor. Also, the last two options are related to the positive displacement compressor turbine, and the first options are related to the centrifugal compressor turbine. Since we are not mentioned which exactly method should we use to make this calculation, let's assume the ASME polytropic method, since we have to define the polytropic efficiency of 0.76. So let's define that efficiency, and we have to provide the information related to the outlet of the compressor. We are given with the compressor pressure ratio, that is 1.5. So choose the option of pressure ratio and give a value of 1.5. So with the given information of the pressure ratio, we can calculate the power requirement to compress the natural gas, or if we were given the power required available, then we could have calculated the pressure developed against that power. Otherwise, if we were given with the performance curve, then we didn't have to provide any of the information above. Rather, we can use the performance curve to estimate the discharge conditions. So based on the capacity or the flow rate, the model can simulate the discharge conditions related to the power and the pressure development. So with this, we are ready to run the simulation, but first have a look on the other options. In the calculations tab, it is possible to define the performance curve to determine the shaft speed. We can make the heat capacity calculations on the rigorous method or the proximate method. There is an option to define the nozzle diameter, that is a suction nozzle of the compressor, and the K factor. On the power loss, we could have defined an appropriate polynomial correlation to determine the power loss in the compressor. In the convergence tab, by default, we are working with the compressor, and that assumes a vapor phase, and it also gives an option to perform the vapor liquid equilibrium, so that if any of the condensate is formed inside the compressor during compression process, it will give a warning of the two-phase formation. Also, in this case, we are not provided with any of the information related to the utility. If the utility information were provided, then we could have used this option to determine the utility requirement, or even we could have determined the cost associated to the compressor operation. With this, we are ready to run the simulation. Let's give a run. The results are available. You can view the results of the block from here, or you can view the results of the summary from the stream results. On the compressor results, you can notice the indicated horsepower, that is 36, nearly 36 megawatt, 36.399 megawatt. The brake power and the network required are still the same. There is no power loss since we have not defined any power loss calculation correlation. The polytropic efficiency is defined as 0.76. The discharge pressure is 82.5 bar. The outlet temperature is calculated as 62.98 degrees Celsius. And if the operation was isentropic, then the isotropic outlet temperature should have been 56.28 degrees Celsius. For me, for this simple case, the power requirement of more than 36 megawatt was beyond the imagination. Then I had run the same simulation in Aspen HYSYS just to make sure the calculation performed in Aspen Plus is cross-checked, and you can view the results from the Aspen HYSYS. The power requirement in Aspen Plus was 36,399 kilowatt, but Aspen HYSYS provided an information of 263 kilowatt. So there is a difference of more than 2 orders of magnitude between the results calculated from Aspen Plus and results calculated from Aspen HYSYS, provided that all the inlet conditions of the stream and the compressor and the method was used the same. I suggest to cross check. One option could be a bug that is hard to imagine for a very respectable commercial software like Aspen Plus. And there, if there is not a bug, if there is any other reason, then as of now I'm unaware of, and I'm unable to explain the difference between the two results. So that's it. How we can simulate a compressor inside Aspen Plus. Let's move to the fourth exercise of the day, that is about multi-stage compressor. The last exercise of this session is about simulation of a multi-stage compressor. Multi-stage compressor inherently includes the compressor, interstage cooler, and the flash column to remove any of the condensate. So the problem statement is a four-stage multi-stage compressor is used to compress air from the ambient condition. We'll assume 1 bar and 25 degrees Celsius as ambient condition for this exercise to a final pressure of 35 bar. The air is assumed to have the following composition, where there is a 76.73% nitrogen, 20.59% oxygen, 1.7% water vapors. So it's a pretty much humid air, 0.919% argon, and 0.0393% carbon dioxide. Each compression stage operates with an equal pressure ratio, and intercoolers are used after the first three stages to cool the air to 50 degrees Celsius. So, for the first three stages, after the discharge of each stage, the steam is sent to an intercooler to cool down and remove any of the condensate in the flash column to lower the temperature to 50 degrees Celsius and drain any of the condensate before entering the next stage. The discharge from the final stage is directly sent to a downstream unit without further cooling. So, apparently, the last stage should be adiabatic. The compressor system utilizes cooling water for intercooling and electricity for compression. So, if all the conditions are like this, then determine the power requirement, heat duty, discharge pressure, and utilities requirement. So, let's enter Aspen Plus to solve this exercise. Let's open a new simulation without any default template. First, define the components of air, that is nitrogen, oxygen, water vapors, argon, and CO2. We are not told about any of the methods Let's appropriately use Peng Robinson in this case. Proceed next to view the binary interaction parameters. Run the simulation. Let's enter the simulation environment. Here first draw the flow sheet. For flow sheet, we have to take this multi-stage compressor. Let's take it, name it as M compressor, and define the inlet stream and discharge stream. Since we are intercooling and there is a humidity in the air, so probably there will be a condensate formed, and for the condensate we need to define an appropriate condensate discharge stream. So for that purpose you can use this liquid knockout. So use 3 liquid knockout streams. Let's name it knockout 1, knockout water 2, and knockout 3. From the fourth stage, since the discharge will be sent to the downstream unit, we don't have to define any of the knockout stream. Let's define the inlet stream conditions. The inlet is at ambient conditions. Let's use 25 degrees Celsius and 1 bar. The molar composition of the air is given. Let's choose the molar composition, where the nitrogen is given as 76.73%. Use 0.7673%. Oxygen is 20.59. 1.7% water, 0.919 argon, and CO2 is 0.0393%. So that is the composition. The sum is very close to 1. We can live with this. We are not mentioned with the flow rate, so we can reasonably assume a flow rate of a mass flow rate of, let's say, 100,000 kg per hour. So with this we can enter the information of the multi-stage compressor. For multi-stage compressor, first we need to define how many number of stages are there. We know there are 4 total number of stages. We need to pick a compressor model, either the isentropic or the polytropic or the positive displacement. For convenience, let's use an isentropic compressor model. We need to define the discharge pressure. Discharge pressure is 35 bar with equal pressure ratio as also informed in the problem statement. If the performance curve was given, then we could have used the performance curve for the rating options. Go to the materials stream option. Here we need to define where these material streams are formed. The KW1 is the liquid discharge stream, and that is from stage number 1. The KW2 from stage 2, and KW3 is the stage 4. So this is how the discharges are from each stage. And we also need to define the phase. So this is liquid phase, make a total liquid, and make a total liquid. So all the streams are defined. Then we need to define the coolers. For coolers, first we need to define the stage where cooler is installed. And for cooler, we are given with the specific outlet temperature of 50 degrees Celsius from all the stages, and we need to define a utility for that as well. So let's create a new utility, and for that we can use a cooling water, and from the drop down you can pick a cooling water utility from the Aspen Plus library. Then similarly from stage 2 we have to define the outlet temperature of 50 degrees Celsius, and the utility is cooling water. Similarly for stage 3, specification is 50 degrees Celsius outlet temperature, and utility is the same. We can define a fourth stage as adiabatic, and there is no duty involved over there, and there is no utility related there. Also, we can define a specification for the power requirement. So for that specification, we can define electricity as the utility. Similarly, for stage 2, for stage 3, and for stage 4. If we were given any isentropic efficiency or the polytropic efficiency or the mechanical efficiency, then we could have defined all the conditions over here. As of now, all the necessary information has been defined. Just have a look on the convergence informations. We are only dealing with the vapor phase. It will perform a vapor liquid equilibrium check, and for the coolers it will perform a vapor liquid equilibrium calculations, and any of the condensate will be discharged from the knockout streams. Let's run the simulation, and the results of the simulation are available. To view the results, let's go to the block results option. Here the discharge pressure is 35 bar, and the total work requirement is 142.54 kilowatt. So assumes around 14 megawatt work requirement for this case. The duties are also given. The cooling duty is minus 10409 kilowatt. Similarly, you can also view the profile for all the stages, where at every stage the temperature is given. From the first stage, discharge temperature is 143 degrees Celsius, 178 from the second, 178 from the third, and 178 from the fourth stage. We have assumed equal pressure ratio. To reach the 34 bar, the discharge of the first stage is 2.4, 5.9 from the second, 14.3 from the third, and 35 from the fourth. Pressure ratio is the same, 2.4 across all the stages. Indicated power for each stage is also given. Brake power is given. Head developed is given, and volumetric flow rate for all the stages is also given. For the cooler options, you can notice duty of each and every stage. The first 3 stages assumes a cooling water to cool down the temperature to 50 degrees Celsius, and adiabatic conditions are assumed for the last stage. Similarly, on the utility tab, you can notice the electricity requirement for all the stages and the cooling water requirements for all 3 interstage coolers. Assuming the default conditions of the utilities, let's have a look on the results of the cooling water requirements. In total, this is the requirement of the cooling water. We can change to a larger units, let's say tons per hour. So in total 1978 tons per hour cooling water is required, and with the default cooling water energy price of 2.12 into 10 per minus $7 per kilojoule, the required cost will be $7.94 per hour to operate the interstage coolers. And similarly, the electricity requirement is also can be found from here. where the default purchase price of the electricity is $0.07 per kilowatt. Depending upon the available informations in your case, you can alter the purchase price and you can view the results of the electricity. Here, the total electricity requirements are 14 to 54 kilowatt, nearly 14 megawatt in this case. Apparently, seems a higher power requirements. To ensure we can cross check with the total flow delivered, and also we can cross check with the calculation method used for this simulation, and we can also cross check with the alternative process simulator. The power requirement is nearly 14 megawatt and it corresponds to a requirement of around $1,100 per hour, and CO2 emission rate is also given against the utility requirement. So these are the informations related to the blocks and the utilities. We can also check the stream results. Here the temperature of all three streams are given. The inlet temperature is 25 degrees Celsius and discharge temperature is 178 degrees Celsius with a 35 bar pressure. When the pressure development is more than 14 bars, the cooling has formed a condensate of 30.95 kilomoles or 557 kilograms per hour that can be taken out of the flash column installed between third and fourth stage. So that's why the discharge flow rate is also less than the inlet flow rate. So if you are interested, you can also view the information of individual phases, liquid phase and the vapor phase. Globally, you can also cross check the phase. For example, the gas phase for the inlet and discharge is the vapor phase, and for the condensate, it's a liquid phase. So this is how you can simulate a multi-stage compressor. So that's it for this session. The remaining task of this session, including the line sizing, will be a subject of some future lecture.